Let's go see what we have today. Today we're going to talk about continuing Gaussian process and also start something new called Bayesian networks, or in general graphical, sometimes they call it graphical perception, sometimes graphical Bayesian methods or graphical Bayes nets or factor graph. They are all showing how we can show probabilistic in a graphical way, how we can show probability, and especially conditional probabilities and chain rule, especially if you have lots of random variables. Writing this up is going to be a big formula, but graphically you can show that very nicely and everybody understand. So we're going to talk about these graphical probabilistic methods. There is two ways to do that. One is Bayesian Bayes net or Bayesian network, and the other one is factor graph. Factor graph is more advanced and much better, but is based Bayes net is Bayes. So I need to tell that first and then move to factor graph next class. We're going to talk about that today. So yeah, let's get started. First of all, let's finish this classification part in Gaussian process. Gaussian process, we talk about that and we mentioned that is another way to optimize a function, and that's amazing. But it has some drawback, some problem that we're going to talk about that. And one of the problem is a little slow right now because computation is big, especially if you want to work with lots of training data, like imagine images. Images are huge. So inverting the matrix is actually computationally very expensive. Is O of n cubic. So O of n cubic means a very high computational, like very expensive, very heavy computational. So that's why we need to find the other ways of Gaussian process for those things. Many people right now working in Gaussian process to make it faster, like some people talking about deep Gaussian process. So deep in the case that change a Gaussian process kind of using GPU or using vector processing. And so many people working in that because of advantage of Gaussian process. The main thing about Gaussian process is that explainable. You can explain it if you get result, even though it's optimizing a function like neural network, like deep neural network, like convolutional neural network. What the Gaussian process is explainable. Another things, it doesn't have problem of overfitting. Overfitting a huge problem in neural network because neural network sometimes learn lots of information, lots of learning data too much. Instead of learning patterns, learn data and noises too, and that's another problem in neural network. But neural network is so popular now and it's fast. Not learning. Learning is very slow, but working is fast. A neural network, you just, if is already trained and you already know the weights, you just give input and get output right away. It's very linear combination. It's very fast and it's very friendly with GPU and vector processors because doing vectors like vector operations and very fast and is very popular right now and working a lot. But we can see example here today, in some cases, is really sucks. It's not good. But still, it's the best now. Okay, so for classification also we can use Gaussian process. For classification problem is a little tricky problem, because in classification you don't have complete function. You need the kind of because we know a Gaussian process is a function optimization problem. So we are trying to find a function like f of x, and this f of x is a latent function, is not in a data. Data is y, I, and xi, and we want to find this latent function that is a function of x plus some sigma. And the point is this sigma is Gaussian, because this is Gaussian process. So everything need to be Gaussian. If something not be Gaussian, we need to actually make it Gaussian. We need to approximate it. We need to make it Gaussian with approximation. So this sigma is a normal distribution with mean of 0 and like a variance sigma square. So yes, this is what we are trying to find. This is a latent function. Latent in a case this function is not in measurements or in the training data. Data is x, I, and y, I. Another thing that I need to mention, Gaussian process consider supervised learning. Consider supervised learning. Supervised learning because like deep learning, like neural network, all family of neural, dense neural network, whatever. Gaussian process is also supervised learning. Is supervised learning means using data to learn. What is learning? In Gaussian process, you are actually learning not just a latent function, but you also need to learn parameters for kernel. Kernel is the main point of Gaussian process, and at the same time is kind of weak point too, because you need to design kernel as well. One of the problem compared to neural network is the kernel. They say, oh, it has kernel too, and changing the kernel changed the problem completely. So knowing the kernel precisely is another issue. Okay, so that's kind of supervising. We consider Gaussian process also kind of supervising. But the point is, in Gaussian process, you don't need to have lots of data like what you have in deep neural network or neural network. You don't need to have that much data. Easily you can fill the gaps of that function, because the point is to find this function, whatever function is this. But in neural network, probably you need to have lots of them, and good one, not biased. But in Gaussian process, because in Gaussian process we are kind of detecting pattern better, detecting patterns better. That's the main point of explaining Gaussian process, is detecting patterns better than neural network. If the data is less, it still can be acceptable. The result can be acceptable. It's not too off, you know. We can see the result in some examples. So anyway, in classification, the problem is that this function needs to create 0 and 1. That's the issue. Because not just 0 and 1, it depends the number of classes. If it's 2 classes, 0 and 1. If it's more classes, need to be like 1, 2, 3, whatever class you have. K, for example. You have K classes. And that might make some part of this, what do you call it, prediction non-linear, non-Gaussian, sorry, non-Gaussian. In that case, we need to do a little approximation. Let's see which part. Okay, let's clean this up. So yes, we need training data, and training data is labeled, but in here we have two classes. We have two classes, so 0 and 1. 1 means, for example, class 1, and 0 means class 0. And the latent function that we are trying to find is f of x, and f of x is Gaussian process. So because we are using Gaussian process, so it's Gaussian process, so it has, for example, 0 mean and kernel k. And this kernel is kind of prior information because we need to know kernel. That's another issue about a Gaussian process. Knowing kernel is important because kernel playing very important role in Gaussian process. And kernel has some parameters like sigma and L. For most of the kernels we have, even some kernels need more parameters. But these parameters called hyperparameters because those parameters can be learned from validation data. They are still labeled. Okay, anyway, this is latent function that we want to find. But the data that we have is a little strange because it's 0 and 1, or is based off the class. So likelihood of actually some class like class 1 given this f of x is not Gaussian. Why is not Gaussian? Because it's 0 and 1, and you need to kind of use another function to make it a probability. So for example, here sigmoid function is a good fit because sigmoid function is like that. This is sigmoid function. Sigmoid function of z is, I think, is 1 over e minus z, something like that, or plus, I'm not sure. This is the sigmoid function. And sigmoid function is the best fitter, especially when you want to make it between 0 and 1. This is 0 and 1, between 0 and 1. If you draw this, this is sigmoid of z, and this is z. In this, and sigmoid function used a lot in neural network too. One of the activation function, very important activation function in neural network is this function. And easily you can get derivative of this, very simple too. Okay, anyway, we're not going to go in that direction. So that makes this probability, and they're going to ask you what this probability called. Is that posterior? Is that likelihood? It can be more. It's one of these two. Is it posterior density or likelihood? Do you know what's the difference between these two? Posterior density and likelihood in conditional probabilities. So in conditional probability, we have something that we want to find, hypothesis x, and some data that we have, we call it z, for example, measurements, and it can be lots of them. This is like capital Z, and this is capital X, means it can be a vector. It can be more than one. So a posterior saying probability of X given Z, that this is the one that we want to find, because easily you can get X out of it with maximizing that, with argmax of that. So this is called posterior. But if you have measurements this side, P of Z given X, this is likelihood. Likelihood of what? Likelihood of that measurements. Likelihood of that measurements. So that's all basic of inference. Inference is that. Inference is computing posterior using given data, that is likelihood. So we want to find posterior given likelihood, and that's likelihood. P of y, because y is measurements. Y, lowercase y I, and x, lowercase I, they are both measurements or training data. Then we want to use it to find the latent function. Oh, let's clean this up. So that's likelihood. This is likelihood. So this likelihood is not Gaussian. Why is not Gaussian? Because of this function. Because to make it probability, we put a sigmoid function. Why we did that? Because this f of x need to create 0 and 1 for us. Because f of x need to create 0 and 1 for us, and 0 and 1 is not even function, you know. And we need to make it function, and at the same time, not just make it function, also make it probability. And sigmoid function do both at the same time. So that's why we have sigmoid function. So this makes it not Gaussian. Okay, that's a problem. Why this is problem? Because if this is not Gaussian, actually posterior is not Gaussian, because posterior is proportion of that. X given z is proportion of pz given x multiplied by what? P of next time if I teach this class, I'm gonna have exam. You're not remembering anything. You should have exam, I think. Okay. P of, what is P of x means? Probability about that unknown. Probability about that unknown. We call it prior. We call it prior. We didn't talk about this. I think we talked many times. Prior info. Prior info is like prediction. Like a robot moving with some dynamic, and we are predicting that it's supposed to be there. That's called prior, P of x. It means some information about x. But the other one is measurements or likelihood, that is updating that. That P of z given x, updating P of x to make a new P of x. Okay, anyway, that's a base rule. That's all basic for basic for Bayesian inference. Bayesian inference. That's a basic of Bayesian inference, and it's one of the important things that you're gonna see in your life is this. Just this. Probability of some unknown given some measurements is equal to likelihood of that measurements given prior information about that state, if consider x a state. Anyway, that's basic of actually class for today as well. Next step of this class today as well. That is how we can show that graphically, because we want to kind of make that easier to solve. We can graphically solve that using BaseNet or Bayesian network, and later factor graph. Factor graph, that the library of GTSAM is coming from that. Georgia Technology SAM, they made this, and that's amazing. That's amazing. Okay, so let's clean this up. So that makes classification a little challenge because it's not Gaussian. And if it's not Gaussian, everything else was Gaussian. So we need to make some approximation. We need to make some approximation to find this actually posterior. This is the posterior. This is the posterior. Okay, maybe you ask me, okay, why you are talking about just one class? What about, here we consider the two classes. So because there is two classes and they are probability, What is the probability of 0? If this is, for example, k, probability of y star is 0, whatever, is 1 minus k. So that's why we don't care about that one. Or maybe you ask me if we have more than one class, what we do in that case. If we have more than one class, we also can use the same way that we were doing in actually neural network. If you are familiar with neural network, what we were doing if we had more than 2 classes. What was the last layer of neural network or deep neural network most of the time? What was that? Do you remember? Is that actually I forgot to. It was the function, I know, but maybe I write the function and I didn't write. Okay. Instead of having this sigmoid, instead of having just 0 and 1, we can have lots of classes like class 0, class 1 to class k. And probability of, for example, here y0 is class k given x star, x and y. In this case, instead of being this, to just specify 0 and 1, it's this function. E power k, I think, what was that function called? Max pool? No, not max pool. I don't remember something like max pooling. Oh, not pool. It's not pooling, but it has some max. I don't remember that. But anyway, for multiple function, we just for multiple classes, we just need to use another function, not sigmoid. There is another function. I don't remember it now. But it's exponential. It's an exponential function. The down part is just for normalization, but the top part is just exponential of x, like a kx in top. And that's going to give you probability of being one of these classes. And this sum up to 1. So for example, you have a class, like in this example, in this project that you're supposed to do, you want to find, for example, possibility of being a road, and possibility of being a side, and possibility of being, for example, grass, like a train type. With the data that you have, you easily can find it because the leader gives you enough information about these areas, and at least based off the depth, you can find that. And in this case, you have multiple of that. You have multiple classes. So you have more than 2 classes. If you have more than 2 classes, when they add them up, they need to be 1. Like for example, you can say, okay, possibility of being a road is 60%, grass is, for example, 20%, and another 20% is, for example, sideboard. They need to add up to 1. That's why we need to have that kind of functions. Okay, so that's the things that we need to do. Let's have one example. In this example, I used one of libraries that already exist in Python. My memory, no. That's in the other, yes, sklearn. I forgot the name. Okay, sklearn. This is the name of the library, learn. Yeah. Name of the library that you can use for Gaussian process. However, there is another one, Gaussian process, GPY. This is another one, but this is for more popular. Anyway, in this example, we are classifying two classes. We just have two classes. So we generated some synthetic data, x0 and y0, and we created how many numbers? 30 numbers, random numbers, and we did 30 for class 1 and 30 for class 0, and we add some noise to them, and we actually stack them together and use RBF function, radial function. It's like a Gaussian, and use Gaussian process classifier is the function inside this sklearn. It's already written. You don't need to just need to use it, and you just need to give the kernel. Is gonna make you actually the class, and then you need to fit it with this training data that you created, and then the rest is just draw it or plot it, and when you plot it, you can see the result. So this is the result. So maybe you ask me, where is the function in this picture? Where is the latent function? But I can ask you, where is the latent function in this picture? You see any function there? It's two-dimensional. Is it two-dimensional? Yeah, it becomes two-dimensional. But x and y. No, it is already two-dimensional. Yeah, it is already two-dimensional. And because we have x0 and x1. We have x0 and x1. But where is the function in this picture? Any idea? Do you see any function? Function need to be like this. Or in 3D should be something like in 3D. Yes?
I don't know if this is right, but like where the concentrated points are, is that like the hump, the wave?
Yes.
Kinda?
Yes, these colors showing intensity. As you can see, they are showing, if you, I put them color, but you can, in 3D, you can give them weight or height. If you like turn that back and give them height, you can see intensity, but one of them is low because it's blue, and one of them is red. So it's showing these two are different. One of them going down and one of them going high. In 3D, you can see that that function is all of these colors. These colors, if you give them height, or right now I gave them weight, that's showing with the color, but as you can see how smooth this color is. It's like a hill. When you do it 3D, it's going to be very clear. That's a function. That's what we detected. So that function can predict any other line, any other points in this space. If I choose one dot, I say, okay, what about this point? What is the probability of this to belong to blue or red? This can give you right away answer because the color is already there, is already detected. So that's the basic of this Gaussian process, and as you can see, it makes amazing result. And you're going to have something like that in your road detection as well. You can have something like this and showing you, so this is the road and the possibility of not, and it's very smoothly moving, for example, from the road to the sideway, for example. Smoothly, showing that smoothness. And this smoothness coming from the kernel. If you choose the kernel, different kernel, it might be different. This kernel that we choose, this is important. Okay, so that was another, let's go for another example. In this example, we do one of the challenging data set, and this data set is called a spiral data set. It has just two classes. Yeah, we can consider two. We don't consider background as another class. So we have blue and red, but as you can see, this class is very actually mixing together because it's a spiral shape. And we just use the same method. We created this and x0 and x1, and then we use same. Actually, we didn't use same kernel. We combined the kernel with some other parts to detect that. So that's the part that it makes it complicated. Changing the kernel is like adding some extra prior to the system. We don't want to have prior. Neural network doesn't need prior. Input coming, output creating. But here you say, oh, this example need another kernel. Because we as a human, we decided that. So we want to make everything like automatically. But in this case, it's something that some supervision needed. Anyway, if we do this, this kernel, and same way, Gaussian process classifier can detect that very nicely. Here is, we detect it. This is a result. This is the result. That's a function. If you look at here, clearly, this is all function. And as you can see, it has two different function. Is it? Or maybe I didn't put the proper. Oh, I didn't put one of the. Yes, this is for. Yeah, I didn't put one of the pictures there, but anyway, it detected. There's two pictures in that. I have the code, but I didn't put that picture. Anyway, in that picture showing detecting these two very nicely. But I did this example for the other class that I was teaching, neural network, and there is a site for like neural network playground that I ask the students to find a neural network with any features, any layers to detect that. This is for just two-layer neural network, but with two-layer neural network, we use these features like a sine, cosine features. They are features that we use. And these features are like those kernels. Somebody choose them. But after this much actually computation and choosing also, they choose different type of neurons. Like some of them, the function like sigmoid function, some of them are tangent function. Anyway, this was the best classification that they had. And that's not good. And I asked them if they increase the number of layers and make it like more, and still you can see that's not good enough. And the Gaussian process is much better. However, I didn't put a proper picture to show that, but is working very nice. And so that's the difference between these two. But is not still popular. Why? Because of this. First of all, scalability. It's not scalable. The matrix becomes n by n because to find the mean, there is some part that you need to invert the matrix. You need to invert the matrix, and matrix inversion is the hardest things or the slowest things in computers so far. And they couldn't find a better way, or maybe they need to design a hardware just for matrix inversion. But right now it's ON2 cost, ON3, ONQ cost, and that's a lot. And in Gaussian process, we need this time. So that's why it gets slow. But neural network, even though the training is so slow because of lots of data, but in action, neural network is very fast and it's very GPU friendly. and it can do like a lots of work at the same time. Another thing is it can support high dimensional inputs, and I'm talking about neural network. But Gaussian process, for example, for some input like an image as an input that has lots of dimension, or LiDAR or audio, is still is not good enough. And kernel is also a problem because you need to choose the kernel as well. And but neural network doesn't have these problems right now. Flexibility is also because Gaussian processes depend on kernel a lot, but neural network is just end to end. You just, even sometimes you don't need to change the number of layers. You just train it, give some input and train it with lots of inputs, and then that train neural network just can go and use in somewhere else. Nothing, you're not changing. Even there is application like for self-driving car. For example, they made a deep neural network and said, okay, you just need to drive with this system 100 hours and then leave it to drive by itself. That's called end-to-end. So the training data coming from your driving. I hope you are a good driver. If not good driver, you're going to train it wrong, you know. You need to drive right. You need to follow all the rules to train the neural network properly. Other than that, you are making, biased neural network. Also, in terms of engineering ecosystem, deep learning has huge industry support. Lots of libraries right now designed for that, hardware, compatible accelerations are designed just for deep neural networks. That's why it's like so popular. And practically, most of companies prefer to use prefer to use neural network. Even though Gaussian process in terms of uncertainty is working better and is explainable, but for some specific applications, we can use Gaussian process, at least the Gaussian process that right now exists. But many people working on that, lots of paper coming out every month regarding that. Okay, so that was the last part about the Gaussian process. Oh, there is no time to start Bayesian network. That's okay, we can start that next class. So anyway, Bayesian network is what we're going to talk about, conditional probability in a graphical way. Okay, any questions? No? So then have a good day and see you Friday. And we're not going to have quiz this Friday. You already had 10 quizzes, so done.
So you actually have stuff implemented?
Implemented stretch.
I have no code.
I guess, sir.
And everyone started talking about having code.